When last we met, we had learned how to take the derivative of logarithmic and exponential expressions when the base was other than e. For example, when the base might be 5. So this was a second derivative problem, and I thought this might take some time, so I decided to put this on another video. I haven't done this one yet, so we'll work through it together, but I'm a little concerned about the product. So I think that logarithmic differentiation is a good first step here. We'll see where that takes us. Maybe this will be good, maybe this will be bad. But when we take the natural log of both sides, remember this is not a calculus step, this is an algebra step. The natural log of a product can turn into the sum of two natural logarithmic expressions, the natural log of each of the two factors. Now, when I'm looking at this expression, I say, well, you know what? Natural log of an exponential expression, don't logs and exponents kind of undo each other? Yes. So let's see what happens if we use a little bit more of our properties of logs. And again, we're not doing any calculus at this point. We'll just pull this negative 3x out front. And again, this part right here is not going to be a product rule because natural log of 5 is simply a constant. So now we're ready to do some calculus. We'll go ahead and maybe over here start taking the derivative implicitly. So 1 over y dy dx equals 2 over 3 plus 2x minus 3 natural log of 5, and then when we solve this for dy dx, we'll multiply this by y. Now it's certainly okay to write that y as this original thing, but I think I'm going to hold off on that because I'm not done with this problem. I would like to now take don't necessarily would like to, but I have to take the second derivative. We have to take the derivative of this derivative. So I'm going to go ahead and take the derivative in this current form. We'll see where that takes us. So if I take the derivative of the derivative in this form, this is a product rule, right? We've got a variable expression times another variable expression. So we'll go ahead and do that. This is, yeah, you could do a quotient rule on that, but let's not. Let's think about this as 2 times 3 plus 2x raised to the negative 1. So that'll be negative out front because of the negative 1 for the exponent. And we'll drop that by 1, that exponent by 1. So it goes from negative 1 to negative 2. And then don't forget the chain rule, multiply by 2. And then the nice thing is that this is a constant, so that just goes away. So this is u prime times v plus u and then v prime is dy dx. All right, so the nice thing is, relatively nice, we know what dy dx is, right? We just found it right here. So this whole thing can be replaced in there. So there's no reason to redo that whole process. We've already done it once, so let's use that answer. All right, so that means that d squared y dx squared is going to equal, well, I'll simplify this, is negative 4 over 3 plus 2x quantity squared times y plus, and then we just have this stuff in here that we don't really have much to do with, 3 plus 2x minus 3 natural log of 5. And then I'll go ahead and replace dy dx with what we know it to equal. And interestingly enough, that 2 over 3 plus 2x minus 3 natural log of 5 shows up twice here. So I'll go ahead and save myself some headache and do a squared here. And then just multiply that. I don't need those parentheses anymore. So one of these factors, this is a minus, one of these factors is from this, the other one is from this, but they're both there, and then we also have the times y. All right, so this might be the most efficient way to do this problem. I'm not 100% sure, but I'll go ahead and factor out the y. And that's going to give us negative 4 over 3 plus 2x quantity squared. And then plus this whole thing squared. So 2 minus 3 plus 2x minus 3 natural log of 5 quantity squared. And if you want to substitute this back into here, that wouldn't at all be a bad thing to do. Or you can leave it like this. I like to leave it like this because it's easier, a little more compact. Fun.